So for objects undergoing orbital motion, we know that the gravitational force is a centripetal force. So that is equal to mv squared over r. And by using this expression, we could actually derive that t squared, where t is the period of the orbit, is directly proportional to radius of the orbit r cubed. And from the same expression, we could also derive that the kinetic energy of the object in orbit is actually gmm over 2r. By knowing the kinetic energy of the satellite, we could now add the gravitational potential energy, which is this expression, plus the kinetic energy to derive the total energy. Hence, the total energy of any object in orbit is negative gmm over 2r. If an object needs to possess sufficient kinetic energy in order to escape the gravitational field strength, then the total energy must be equal to 0, which in this case means that minus gmm over r plus half mv squared, where v is the escape velocity, must be equal to 0. Let's now take a look at how the various energy changes with r for an object in orbit. So the first one is your gravitational potential energy, which is negative gmm over r. The next one is your kinetic energy, which is gmm over 2r. And finally, the total energy is negative gmm over 2r. Finally, let's take a look at geostationary satellite. Geostationary satellite is a satellite that rotates about the plane of the equator. Direction is the same as that as Earth, and the period for it to complete one revolution is 24 hours. So you can see the path of the geostationary satellite, in this case, demarcated by actually the red dotted line. The advantages of geostationary satellite is that permanently it can be above a certain point, and there's also large area coverage. The disadvantage is that it needs to be a certain distance away from Earth, so therefore its resolution is low and is far away from the Earth's surface, and therefore more expensive to launch. Finally, for questions involving binary star. In binary star questions, you have both massive planets or both massive stars orbiting around a common point known as the common center of mass. So in this case, C is the common point. Hence, you can see that when Y orbits to this level at here, Z will be moving, Z would have moved to this location here. So they are always at an equal distance away from each other. And when Z orbit to this position, star Y would have orbit to this position. Finally, when star Z goes into this position, star Y will be at this position. Again, they are same distance apart. So in terms of the gravitational force acting on each other, they are equal. And since action equal to reaction, that gravitational force that acts on Y is actually the centripetal force. And the same gravitational force that acts on Z is the centripetal force that acts on star Z. What's more important when you solve this question is that you need to note that both the stars have the same angular velocity.